Hi, PC. This is Mr. Stanley again, and today we're going to be talking about the different states of matter and their phase changes. I'm going to go over the difference between solids, liquids, and gases, and talk a little bit about how we can change from one state to the other one. All right, so states of matter and phase changes. This is kind of a good introduction to chemistry because most of you, I'm assuming, are familiar already with kind of the idea of solids, liquids, and gases. So we're going to go into it a little bit further in depth today, talk a little bit more specifically about the differences between these three states, and talk a little bit about why they get formed at the different temperatures that they do. So the first thing that we're going to talk about in terms of these states of matter is a little bit more kind of scientific theory. It's this idea known as the kinetic molecular theory. So the kinetic molecular theory is this idea that all of matter, so matter is just a fancy scientific word meaning stuff, essentially. And so the kinetic molecular theory says that all matter is made up of these tiny particles that are in constant motion. They're constantly moving around, jostling around one another. So as the temperature of a piece of matter goes up, so does the kinetic energy in these particles. So the kinetic energy, or the motion of these particles, how they are moving, increases as the temperature of a piece of matter increases. Excuse me. So as a piece of matter gets hotter and hotter and hotter, as stuff gets warmer, the particles that are inside that matter will start moving faster and faster and faster. Maybe they'll just be kind of vibrating in place, or maybe they'll be zooming all around a room. But kinetic molecular theory says that everything is made up of these tiny particles, and as the temperature goes up, these tiny particles move faster and faster. So there are 4 overall states of matter, but there's really 3 that we're going to focus on today. The 4th one is kind of complex. So we're just going to briefly talk about that one. But there's 3 that you absolutely have to know about, and that's solids, liquids, and gases. So we'll start off talking about the solids. This is our lowest energy state of matter. So the particles in a solid, as you might imagine, they're very structured, they're very bound together, so they can't really move a whole lot. They can vibrate around each other, so they kind of are vibrating in place right next to each other, but they're not really moving around each other all that much. So these guys have the lowest amount of Ke, the lowest amount of energy. Remember, that's what the E stands for in this Ke. Low energy in our solids. So solids, because they're so structured, because those particles are so tight together, they have what's known as a definite shape and a definite volume. Now, what I mean by definite is that it is a set shape, a set volume, right? So my computer mouse right here, this is a solid, and it has a definite shape. So no matter where I put this computer mouse, whether I put it in front of the camera, I put it down next to me on the table here, if I took it and put it in like a big vase, it would still be the same size. It would still be shaped like this kind of round, wobbly computer mouse. And it always has the same volume, meaning it will always take up the same amount of space. So a solid is essentially always the same no matter where you put it. So that's kind of what's being demonstrated in this picture over here. We have this solid made up of these blue particles, and it's inside of kind of this glass vase, but it's still staying in this cube altogether. It's not spreading out and kind of covering the bottom of the vase, and it's not getting any bigger or any smaller when we put it in there. It just stays the exact same as it is. So that's what we mean by definite shape and definite volume. It does not change how it looks, and it does not change how much space it takes up. So that is our lowest level of energy, is our solids. If we go up one level, so if here is like our energy levels and solids are down here, then our medium level energy is liquids. So liquids have a higher amount of energy than solids. They don't have the most energy. The particles move around a lot more than solids, right? So unlike a solid and a liquid, we're not completely bound together. The particles can kind of move over each other. You know, they have those waves going on in the ocean, and that's those particles moving over and around all each other. But they're still kind of close together. They're not completely spreading out across the ends of the area. They're still kind of staying close. They're just a lot more mobile than our solids. Liquids have an indefinite shape, right? If I take a bottle of water and I open it up and empty it on the floor, is the water going to stay in that nice bottle shape and just kind of plop out onto the floor? No, it's going to completely spread out along all of the floor. If I somehow am able to like scoop up that water and dump it all into a sink, it's going to start filling up the bottom of the sink. But they do have a definite volume. So no matter where you put this liquid, if you have a cup of water and you put it into a big saucepan and then you pour that into a sink and you scoop it out of the sink back into the cup, it's still going to be a cup of water. So the shape changes depending on where you put it. If you fill this up, you're going to get a big kind of cylinder of liquid. If you pour it all into a big like fish aquarium, maybe that's like a big cube, so you get a big cube of liquid. It just fills up whatever container that it's in. It doesn't have a set shape on its own. It just goes and fills up wherever you put it. But it'll always be a set amount. 1 cup in a measuring cup is the same as 1 cup in a pot, which is the same as 1 cup emptied out onto the floor. It's always the same amount of liquid. So definite volume, same amount of volume, but indefinite shape. And then finally, the highest level of matter that we're going to talk about, the most energy. So if solids were our lowest energy, liquids were our medium energy, then our highest energy is going to be gases. So gases have the highest amount of kinetic energy. The gas particles that are all around you right now are zooming all over the place. They're constantly in motion, constantly zooming around all around you. They're completely separated from one another. So unlike solids and liquids where the particles will kind of stick together, gas particles will completely separate out and spread across whatever container that you put them in. The interesting thing about gases is that they both have an indefinite shape and an indefinite volume, meaning that not only do they take the shape of the container that they're in, just like water, but they also will expand in order to fill up the entire amount of container that you put them in, right? If you have a like Tupperware and it's just open to the air and then you put the lid on top of it, it's not like all of the gas and the air is just going to go and condense down in like the corner of the Tupperware, right? It's going to be completely spreading out and taking up the whole area, the whole volume of the container. So gases, because they're so separated and because they're so light and constantly moving around all over the place, they don't have a set shape and they don't have a set volume. They'll just expand out to take up however much room that they can in whatever container that you put them in. So that is our solids, liquids, and gases. Solids, the low energy that always are in the same shape and the same size. Liquids are medium energy, don't have a set shape, they have an indefinite shape, but it'll always be the same amount. And gases have an indefinite shape and indefinite volume. They're the highest energy and they will completely spread out from each other in order to take up however much room they can in their container. Plasma, we're not going to really worry about it. It's another state of matter. Usually you get it either through very specific like electrical or chemical reactions, or in very extreme situations like inside of stars, you get a lot of plasma. But we're not really going to worry about it for this class. We're just going to focus on solids, liquids, and gases. So one interesting thing about things like solids especially is that they will slightly, tiny bit change their shape and their size depending on the temperature. So solids and liquids and gases, for the most part, all tend to expand and get a tiny bit bigger when you heat them up, and contract when you cool them down, get a tiny bit smaller when you cool them down. So as you increase the temperature, remember earlier we talked about the kinetic energy, so the motion of those particles, and that motion goes up with temperature. So those particles tend to spread out a little bit as they get hotter. This is what early thermostats were actually based on. So they had two strips of metal, one that was really sensitive to heat and one that was really sensitive to cold. As a room got warmer, the metal in the strip would expand a tiny bit, and that tiny expansion would push the little lever, the little indicator, up towards the hotter side. And as the house cooled down, the metal would contract a little bit and move that way and pull the indicator back down to the cooler temperatures. So more heat, more energy, more movement, and more space. And the opposite when you cool it down. Less energy, less movement, so it shrinks a tiny bit. So things that are solids, liquids, and gases have all these properties, but that doesn't mean that they're going to be solids, liquids, and gases forever. We can change states and go from one to the other if we put in enough energy or take away enough energy. So first, we're going to talk about what are the different names that it's called for when we increase or decrease our energy, and how can we measure that over the course of something going from completely solidified to heating up all the way to turning into a gas. And we'll go over what some of the steps are in that process in a little bit more detail. But first, what is it called when we go from a solid to a liquid to a gas to a liquid or to a solid? So the first couple of these you've probably heard of before. The first one is melting. And melting is when you go from something that is solid to something that is liquid. So think about an ice cube. If you sit an ice cube on your kitchen counter, it's going to start as a solid piece of ice, but you leave it out there for several minutes, and eventually it will melt and turn into liquid water that's sitting on your kitchen counter. If we go the other way, if we take that liquid water and put it back into our freezer, then that will freeze. So freezing is just going from liquid to solid. So whenever we have something that's in its liquid form and we cool it to the point where it forms a solid, that is freezing. So we call the temperature at which this happens for a material either the melting point or the freezing point, depending on if you're kind of talking about getting hotter or getting colder. These will both be the same. So for example, water is probably the most common liquid and solid and gas that we experience on our daily basis in our normal lives. Water has a melting point or freezing point of 0 degrees Celsius, and I use Celsius because in science we stick with the metric system. But in terms of Fahrenheit, that is 32 degrees Fahrenheit. So if you get water and you take it below 0 degrees Celsius or 32 degrees Fahrenheit, at -1 degrees or at 31 degrees Fahrenheit, it will start freezing. It'll start turning into ice. If you take ice and put it somewhere that's 1 degree Celsius or 33 degrees Fahrenheit, it will start melting into a liquid. So the melting point or freezing point just describes the temperature that melting and freezing happens. All right, so we've gone from solid to liquid and back. We can also go from liquid to gas and back. So vaporization and evaporation both describe the process of going from a liquid to a gas, just in a slightly different way. Vaporization, you've probably heard of before as boiling. So this is when we take liquid and we heat it up to what's called the boiling point. And it'll start, because of all this heat energy that it's getting, it'll start continuously turning from a liquid into a gas. And we call this vaporization. That's not the only way that liquids can turn into gases, though. We can also have evaporation. This is when we get that change still going on, but it happens below the boiling point. So, for example, after a big rainstorm, the next day it's nice and sunny and warm outside, but because of all the rain yesterday, you see these big puddles of water all over the street. A little later on, you go back outside and the puddles of water are all gone. What happened to them? Nobody came by and picked them up with a sponge or paper towels or anything like that, because it's the outside, so who cares? And obviously it didn't get up to the boiling point outside, because that would be 100 degrees Celsius or 212 degrees Fahrenheit. Obviously, if it was 212 degrees Fahrenheit outside, then we have much bigger problems to worry about than just liquid changing to gas. So it never got to that point. It got to, maybe if it was in the middle of July or August, maybe 102, 103 Fahrenheit outside. But this water still disappeared. And that's because liquid can change to gas slowly over a long period of time through this process of evaporation. It's due to some of the different chemical properties of liquids and gases that we're not going to super get into today. But just know that vaporization and evaporation both indicate something going from a liquid to a gas. Vaporization is one that happens at a really hot temperature at the boiling point of the liquid. Evaporation is what happens when we're not at that boiling point, but we still get this slow change over time. We can also go from a gas to a liquid through a process called condensation. So if we have all these gas particles in the air, if we cool them down enough, they'll start clumping together and forming a liquid, and we call that process condensation. So this is actually what happens when it rains outside. So up in the atmosphere, there is a whole bunch of of gas water, known as water vapor, that's moving through the upper atmosphere. Now, up in the atmosphere, it gets pretty cold, so the water particles will start to condense together and form clouds. So those big white fluffy clouds that you see floating along in the sky sometimes, those are just water that's condensed together in the atmosphere. If a lot of that water condenses together and it gets cool enough in the atmosphere, then that water will condense to the point where it starts making little liquid droplets that become so heavy that they fall down to the ground, and we call that rain. So condensation is when we have this water vapor that cools down, becomes liquid water, and then we see that fall out of the sky as rain. So anytime we have a gas that gets cooled down to the point where it starts turning into a liquid, that is condensation. The same thing happens if you have a really, really cold glass of water that has a bunch of ice in it. You leave it sitting out for a little bit, and all of a sudden, the outside of the glass feels kind of sweaty, feels kind of wet, right? That's not happening because a tiny little bit of liquid is leaking out of the glass. That's happening because the water and the ice in the glass is so cold that the water vapor directly surrounding the glass on the outside starts to cling and condense on the outside of the glass because of the low temperature. That is also condensation. We have water vapor, that's a gas in the air, condensing together to form liquid that covers the outside of that glass. You might think that we're done here because we've gone from a solid to a liquid through melting. We've gone from a liquid to a gas through vaporizing or evaporating. We've gone from a gas to a liquid through condensation, and we've gone from a liquid to a solid by freezing. So what else could there possibly be? There's one final phase change that doesn't happen a lot, but it is something that occurs in nature, and that's called sublimation. So sublimation is one of my favorite science words just because it sounds cool to say. But what it means is when we go from a solid directly to a gas. We completely skip over the whole liquid phase in the middle. So where most people have experience with sublimation is with dry ice. So dry ice is something that you can buy at the store. It comes in those really tight package containers, and when you open it, it's super cold and all of this kind of smoke and fog starts coming out. Dry ice is actually frozen carbon dioxide gas. So it's CO2 gas. This dry ice right here, it's CO2 gas that has been chilled to about, I think it's negative 112 degrees Fahrenheit. So super, super, super cold. When you expose that carbon dioxide gas to the air, say it's 70 degrees in the room that you're in, the solid carbon dioxide is at negative 112. The room is at 70 degrees. That's almost a 200-degree difference in temperature. So the CO2 block, like this guy right down here, gets so hot that the solid just spontaneously starts coming off as a gas. So it gets heated up to such a degree that it just skips over the liquid step entirely and goes directly to gas. This is what we call sublimation. Getting so hot that our solid goes directly to a gas. So this little chart is a really useful one for kind of keeping track of all things. We start in our solid. We heat it up to the point where the particles start to spread out a little bit and they become liquid, where we melt. So we go from a solid, melt into a liquid. We then heat up that liquid some more, and through evaporating or vaporizing, we become a gas. If we take that gas and cool it down so that the gas particles start joining up with each other, we condense it, it goes through condensation and becomes a liquid. And finally, if we chill that liquid to the point where it starts turning into a solid, then we have frozen that liquid. It's gone through freezing. And then on the other side, if our solid gets so hot that it kind of automatically turns into a gas, that is sublimation. So those are our major phase changes: melting, freezing, condensing, evaporating or vaporizing, and sublimation. So one way how we can show how the energy or the temperature of a substance changes as we heat it up over time is through something called a heating curve. Now with our heating curve, there's two different aspects of energy and of heat that we need to think about. There's kinetic energy, which I've mentioned already. This is that energy that has to do with the particles and how they're moving. So remember, as the temperature goes up, the particles move faster and faster and faster. That is kinetic energy, motion energy relating to these particles based on temperature. There's also something called potential energy. Potential energy has to do with how big the space between these particles is and how much energy it takes for there to be more space between the particles. So this potential energy is more related to phase changes, or going from a solid to a liquid to a gas. So each time we change phase, we go from one energy level to the next one, from a solid to a liquid. Those super tight solid particles that were like super close together before, they're super packed in with one another, right? So imagine this is our solid. when we take it to a liquid, remember, when our energy level goes up, that means that our particles are a little bit more spread out now. So in order to kind of pull those particles apart from each other, to go from this super condensed solid into this more spread out liquid, that takes a lot of potential energy. So we're not actually getting hotter going from a solid to a liquid. We're not increasing the temperature anymore. We're at that, in this case, the melting point, right? Right, MP for melting point. So we're at the melting point. We're at that 0 degrees Celsius or 32 degrees Fahrenheit. And so now, instead of getting hotter, that energy that we're getting is going into spreading these particles out from one another. So we need energy in order to spread those particles out, just like we need energy in order to make the particles move faster through temperature. So I know that explanation maybe isn't making things super clear, but I'll show you a chart in just a second that hopefully will kind of explain things a little bit more. So let's say that you take a big block of ice, you stick a thermometer into it, and you put it on like a saucepan on top of your stove, and you turn on the heat. This ice was at a really, really cold temperature, negative 20 degrees Celsius before. And so initially what's going to happen is the ice isn't going to start melting right away. It's still a solid and it hasn't reached that melting point yet. So instead, the temperature of the ice will start to go up. And remember, as temperature goes up, so that's what the little kind of ramp right here is. Our temperature is on the x-axis right here. So as this line goes up, the temperature goes up. And then this line down here is just showing the time that's gone by. So as the temperature goes up, this is just the kinetic energy. So our block of ice is still a block of ice. There's no water yet, but the ice particles are starting to vibrate faster and faster and faster. Eventually, we reach this melting point, 0 degrees Celsius in the case of water. And now we have this flat line all of a sudden, right? For several minutes here, the temperature of our water isn't going up. Why is that happening? Because we're going through that phase change. We're changing from a solid to a liquid. So we're melting the ice, and that takes a lot of energy. So the energy that we're getting from the stove in the form of heat, instead of making the particles vibrate faster and faster and making the temperature go up, now, instead, it's making the particles spread out from each other more and more. And that's what this potential energy, this PE right here, is referring to. I should probably change the color of this guy. Let's see. Let's do blue. That's what this PE is referring to, is the energy that's going into spreading the solid particles away from one another, turning them into liquid particles. Once we do that, and we've got our big ice block completely melted, then all that water that's sitting in this pan is going to start heating up once again. We're still on a stove. We still got heat energy coming in from the bottom. And so our liquid now, its kinetic energy and its temperature are going up. So the temperature is going up. Our liquid particles are moving around each other faster and faster and faster. And so that's what's happening between here and here. So we had our solid getting hotter, and then we had no change in temperature as we went from a solid to a liquid, and now we have our liquid getting hotter. Then, as you probably have noticed by now, we have this big stretch of flat line right up here. This is, instead of melting, going from a solid to a liquid, Now we're going from a liquid to a gas over here. What is it called when we go from a liquid to a gas at this hot temperature, this boiling point up here? It's called vaporization, or you can just call it boiling too. So as we're boiling, we're going from a liquid over here to a gas over here. So this is gas over here. But in order for that change to happen, we have to put in a lot of energy in order to separate these particles all the way apart from each other. Because remember, liquids, the particles are still kind of remaining close to each other, but in a gas, the particles are completely spread out. How do we spread out those particles? We put a lot of energy into the potential energy during this change in order to kind of break apart the final bonds that the liquids had with each other and completely separate out those particles and turn them into gases. So that's what's being shown on this heating curve. We start off as a really cold solid. We start to heat it up so our temperature goes up. Eventually, it hits a specific temperature called the melting point, which for water is 0 degrees Celsius. Once we hit that, we then start putting energy into separating out the particles from each other. So we are melting, in this case, going from a solid to a liquid. Once we've completely melted, we take that liquid and heat it up again. So our temperature starts going up and up and up once more. The liquid particles are getting more and more and more energy, more and more and more movement, until finally we hit another specific temperature. In this case, 100 degrees Celsius, the boiling point for water. And now, as the water is boiling, it's staying at 100 degrees Celsius. It's not getting any hotter, even though it's sitting on the stove, but we're changing all of that liquid into a gas. So we're boiling, or we're vaporizing, all the liquid in our pan and turning it into a gas. Once we've gone through that whole phase change process, we've taken all of our liquid and turned it all into gas. Only then will the gas around the burner start to heat up and have those particles move even faster. So that's why we have these periods of flat lines on our heating curve in between the times when our substances were getting hotter. These flat lines are showing us when we're changing phases from a solid to a liquid or a liquid to a gas. And the temperature isn't going up because instead the energy is going into the potential energy of separating the particles away from one another. The heat of fusion and heat of vaporization just are specific amounts of energy that it takes to change from solids to liquids or liquids to gases, but we're not really going to worry about those for this class. The main thing to know is our solids, liquids, and gases. What are their properties in terms of energy and shape and volume? What is it called when we change phase from one to the other, when we go from a solid to a liquid, or a liquid to a gas, or a gas to a liquid, or a liquid to a solid, or a solid to a gas? And then finally, how do you read the phase change diagram? How can you look at that heating curve going up and up and up and know what's going on at the different stages? The reason why this is important is because that's what your homework is going to be over. So your homework is going to be this 2-page worksheet on the states of matter and phase changes. The first part of it kind of describes some of the stuff that we talked about earlier today in terms of solids, liquids, and gases. Again, you can kind of skip the plasma section. We don't really need to know about those guys. So for the first part of it is you have these 3 different pictures of particles, and you have to label whether they are a liquid, a solid, or a gas. You then have this little triangle of solid, liquid, and gas down here. And so you have to label each arrow in between them with the correct name of the phase change that goes there. And then finally, we have this heating diagram, like we were looking at a little bit ago, labeled from A to F with the energy on the x-axis down here and the temperature on the y once again. And so for each one of these, you essentially have to be able to answer these questions in terms of what's going on in between two different letters, what state, solid, liquid, or gas, are we at each one of these letters, and why is it sometimes that we're increasing temperature versus staying the same temperature in between like A and B, B and C, C and D, etc., etc. So hopefully helping me guide you through it a little bit more helped you make some sense out of it. As always, if you have any questions about it, you can either email me, text me, or ask to have another Zoom chat. You can also come to one of our open office hour Zooms. I'm going to be essentially just in front of the camera for a little over an hour to be there in case people want to drop in and answer questions. And remember that when you're working on the worksheet, I'm assuming most people are going to be kind of copying it down into a blank piece of paper, writing it down on their own, and then taking a picture of it, and you can send that picture either to my email, you can text the picture to me, or you can upload the picture directly to the assignment under the Google Classroom. Either way is a totally valid way of turning in your work. If you have any questions, please let me know as soon as you can. Otherwise, I will see you soon for our next set of notes.